students, I'm going to go ahead and go over some stoichiometry stuff with you guys. Sorry, I'm going to have my camera off. I'm not really camera ready right now, but we're going to make it work. So these videos are going to go over stoichiometry using our PowerPoint. So hopefully things will start to make a little bit more sense. So first, I want us to take a look at chemical reactions and what they mean. We just got done with our reactions unit. So we know that we balance our equations, that we have the right numbers of atoms on both sides of the equation. So first off, we want to always start with balanced reactions. So looking at this reaction, I know that I've got to have 2 water molecules to balance the oxygens. Then I need a 2 in front of my hydrogens over there. And it asks how many water molecules can be made from 6 molecules of H2 and 3 molecules of O2. I'm going to share this simulation that's linked here so that we can see. So here you go. With our balanced equation, it says we need 2 hydrogen molecules for every 1 oxygen. So you can see that when we have that, we're going to make 2 water molecules over here. And the question asked, how much water can we make if we had 6 hydrogens and 3 oxygens? So our answer is we can make 6 waters. That ratio is always going to be the same. So if 2 hydrogens and 1 oxygen make 2 waters, and we triple the amount of our reactants, we're going to triple the amount of products that we can make. So in your boxes on your paper, this is the representation that you should be drawing for your reactants in the left box and the products on the right box. Okay, so let me go back to the PowerPoint here. Here we go. So let's look at this reaction. This one is the synthesis of ammonia. So first off, we've got to do what? We've got to balance our reaction. That's right. So we've got to get a 2 here in front of the ammonia to balance out those nitrogens, which means that we need a 3 in front of the hydrogens. So it says how many ammonia molecules can we make from 2 molecules of nitrogen and 6 molecules of, that should not say 6 molecules of ammonia, that should say 6 molecules of hydrogen. I apologize for that, 6 molecules of hydrogen. So make your prediction while I switch over here and share that simulation again. So this time I'm going to switch to ammonia. And it said that we needed 1 nitrogen for every 3 hydrogens to make 2 ammonias. And so our prediction, have we predicted how much ammonia that we can make from 2 nitrogen molecules and 6 hydrogen molecules? Let's see if you were right with your prediction. There's 2 nitrogens and 6 ammonias. So we've doubled essentially the amount of reactants we needed because we went up to 2 nitrogens and we went up to 6 hydrogen molecules. You can see up here our balanced equation. And it shows us that we could have made 4 waters in this sense. If we double our reactants, we're going to double our products. That's what stoichiometry is essentially. So I should go back here so we can finish up. So what is stoichiometry? Stoichiometry is looking at our balanced reactions and coming up with quantitative relationships between the substances involved. It's not just looking to see how much reactant we have and how much product we're going to end up with. It could help us to determine how much reactant we need from, another reactant that we have. It can tell us how much reactant we're going to need in order to produce a certain amount of product. So the coefficients are going to become very, very important in these stoichiometry problems. So stoichiometry is just like a recipe. So take a look at this here. This is our recipe, if you will. 1 banana plus 5 strawberries is going to give us 2 smoothies. So I want to know how many smoothies can we make if we have 2 bananas and lots of strawberries? Well, remember, this is the same thing we were just looking at. If we double our reactant, we're going to do what to our product? We're going to double it. So we should be able to make 4 smoothies because that ratio is 1 to 2. Now, how many smoothies can we make if we had 25 strawberries and lots of bananas? So what are we doing to that reactant? We're multiplying it by 5, so we want to multiply our product by 5. We can end up with 10 smoothies there because that ratio is 5 to 2. So we're going to be using mole ratios. Mole ratios is taking a look at those coefficients from our equation and writing it as a conversion factor, which we've been using all throughout mole conversions, where we end up with one thing over another thing, such as this. 2 moles of aluminum over 3 moles of bromine. That relates our two reactants together in this particular reaction. We could do the same with a reactant over a product. 2 moles of aluminum would give us 2 moles of aluminum bromide. Okay, so let's practice writing some mole ratios. So here we already have a balanced chemical equation here. It says that we're going to write some mole ratios. Can you write ratios like they do in math with the colon in the middle? Sure. The reason I don't write mole ratios that way is because we're going to be using them for our dimensional analysis mole conversions. And I want you guys to get in the habit of seeing those written as essentially fractions, those conversion factors. So if we have butane to carbon dioxide, that means we're going to have our 2 moles of butane over 8 moles of carbon dioxide. If we have butane and oxygen, we would end up with those 2 moles of butane over our 13 moles of oxygen. And then oxygen to carbon dioxide, what would we end up with on the top? Yep, 13 moles of O2. What would we put on the bottom? Those 8 moles of CO2. And then the last one, letter D, carbon dioxide and water, what are we going to put up on the top? 8 moles of CO2, and then the 10 moles of water would go on the bottom. So this one is another example. This time we have to write our balanced reaction. So pause this, try to write this reaction yourself, because you are still going to have to remember how to write balanced reactions for your stoichiometry test. Give it a try. Start the video again so you can check your work. So the balanced reaction here for aluminum chloride reacts with oxygen to form aluminum chlorate is right here. Now check your words, make sure you have the right balanced equation, and then try to write these mole ratios on your own. So pause it, write these mole ratios on your own, and then restart it so you can check your work here. And there's your answers at the bottom. All right, now, the first kind of problems we're going to do in stoichiometry are mole-to-mole conversions. So we're going to use those mole ratios we just talked about and dimensional analysis, which is the same process we're doing during mole conversions, to help us to switch from one substance to another substance in our conversion. So let's take a look at this. How many moles of CO2 are produced from the combustion of 7.3 moles of C4H10? Now remember, combustion means O2 is a reactant, and we're going to make water and carbon dioxide. So there's our balanced reaction, okay? Now it says up in the top right, we're going to circle what we start with, and we're going to box what we're trying to find. That's just so we can have our visual in our reaction itself. So we're starting with butane, and I'm going to put how much we start with over that, 7.3 moles of that, and we're looking for carbon dioxide. So I'm going to box that and put some moles over there. Again, this is so we have our reference and so we can keep track of what we're doing, where we're starting, where we're ending. When you start your dimensional analysis, the thing that you always start with is your given. So we're starting with 7.3 moles of C4H10, okay? We know we're going to multiply that by some kind of conversion factor. Ignore the dashed line here. That was the best I could do. So remember, whatever unit we start with, those units have to go at the bottom of our conversion factor. So I have to have moles of C4H10 down here. If you're already in moles and you're starting with moles, you're going to go ahead and put that 2 from the balance equation right there, because you know you're going to have to switch from moles of butane to moles of carbon dioxide. This is where we use our mole ratio that we were just writing, because our reaction tells us that 2 moles of butane gives us 8 moles of CO2. That's why we're allowed to do this. Since we're looking for moles of CO2, and that's up here at the top, we can go ahead and solve. So you're going to plug this into your calculator, 7.3 times 8, because it's on the top, divided by 2 because it's in the bottom, and that's going to give us 29.2 moles of CO2. But remember, we always base our sig figs off of our starting value for these kinds of problems, so we only need 2 sig figs. So we're going to have 29 moles of CO2 as our answer. Let's take a look at this next one. How many moles of iron are produced when 1.75 moles of iron 3 sulfate reacts with zinc to produce zinc sulfate and iron? So here's our balanced reaction already. So remember, we're going to circle what we're starting with, put what we're starting with. So we have 1.75 moles of that. And we're looking for iron. So in a box what we're looking for and put what I'm looking for, the moles of iron up at the top. So when we start our dimensional analysis, I always start by writing our given. So we're starting with 1.75 moles of that Fe2SO4 We have to multiply it by conversion factor because we're changing from iron 3 sulfate to iron. So whatever unit I start with, that unit has to go at the bottom. I've got to have moles of Fe2SO4 Now, how many moles am I going to have? I'm just going to have 1. This 1 is because the coefficient of the Fe2SO4 in the balanced reaction is 1. Okay? Because I'm already in moles, so once I'm in moles in my stoichiometry sequence, I'm going to use the balanced reaction to switch from moles of Fe2SO4 to moles of iron. How many moles of iron am I going to put up here on the top? I'm going to put 2. And I'm going to go ahead and multiply because my 2 is in the top. Now, when your calculator spits out the answer, it's going to give you 3.5 moles of Fe, but I want 3 sig figs. So I'm going to have to record my answer as 3.50 moles of Fe. So I'm going to have you guys practice these 2 problems on your own. Here are your answers, so that way you guys can check your work and make sure you know what you're doing. If you have any questions about mole-to-mole conversions, just let me know. Remember the importance of showing your work. It's so important in this unit to show your work, including all of your units and symbols, because we are switching those symbols in the middle of our problems this time. Okay, so important. Let me know if you guys have any questions about those mole-to-mole conversions.